So this is our home screen. When you start off with Paradise, you get our home screen. It shows you what are our most recent results for faults and SOMs, our most recent PCA results, our most recent geobody results. And you can, from here, it's really easy. You can just right click, open in 3D Viewer. So here's Maui, it's offshore New Zealand. I'm just going to click on this, I open it up. This is one that actually has a channel. So here's a self-organizing map. I can show the color selector. And it shows you all the different neurons, right? So what neurons, and you can kind of see already what neurons are going to represent your channel. So look through here, and watch, I'll zoom down in this section, and you'll start to see this channel. You can see it right there start to pop up, coming through here. Yeah, there it is. See that channel? Yeah, so that self-organizing map does a really good job of highlighting, and if I wanted to, I could isolate the neurons that make up that channel and generate a geobody from it. So it's a good example of just a self-organizing map. So let me show you how to run it. So it starts off with machine learning, and all of our stuff, our thought flows go like this. So I'm going to click on my self-organizing map. Let me reset thought flows. All of these start from left to right, so they're really easy to run. I want to run a SOM. I want to create a SOM. Time. And choose Niobrara. It's this one right here. I then choose which attributes. So I can choose all the different attributes that I want to run. You can launch self-organizing map directly from PCA, and it'll all be pre-selected. So I already ran PCA, I selected these, you click launch SOM, it'll take you to this screen with all the stuff that you already chose pre-selected, right? So click this, click OK, choose the data delimiters. Now there's two different data delimiters. The harvesting area, so this is where I want to train my SOM on, and the classification area. So you can train on the samples around your wells or in a small subsection, or you could train on all the data, and it'll train via a winning line. So if you train on all the data, it'll cut that data up, it'll take it inline, then move 20 inlines and take it inline, move 20 inlines, and it'll do a statistical fit of which inline is the best SOM training, and then classify the whole volume based off that SOM training. The best way to think about harvesting is it's going to put the location of the neuron centers, find the location of the neuron centers, and the classify is you plot the same attributes and then give it a winning neuron, which neuron won, based off those attribute centers, or those neuron centers. Choose my data delimiters. Here we go. Okay. Choose the parameters. I want to run a 10 by 10 or an 8 by 8. This is all the different neuron topologies. How detailed do you want it? I've found that structural interpretation likes lower topology, and reservoir interpretation you want higher topology, because you're really trying to delineate the samples. Click parameter set, click assign, run my SOM, click activate, and then save. Okay. Now you asked about PCA. I can come down here to enter my PCA results. It's the same blue button thought flow, but I'll just go straight to the end. Let me see if I have PCA results here. All right, so here's an example of my PCA. So here's eigenvector 1, and I can tell from eigenvector 1 that sweetness and envelope, acoustic impedance, and Hilbert made up the majority of my eigenvector 1 out of all of it. This is a 15-dimensional crossplot. Now I'm looking at the next eigenvector, eigenvector 2, instantaneous frequency and thin bed made up the majority component of eigenvector 2. Eigenvector 3 is my amplitude and my normalized amplitude. Now that actually makes a lot of sense that those two have similar eigenvectors and eigenvalues. Eigenvector 4, we already have normalized amplitude, so remember this is a rotation in n-dimensional space, so the distribution of normalized amplitude is similar to between 3 and 4, so we don't need to add it again. And then bandwidth was eigenvector 5, and instantaneous Q. This is what you're talking about, instantaneous Q being one of them, eigenvector 6. But I'm just going to go ahead with these 8 attributes, set up a SOM, and then you click yes, and then it's already ready to go. Really easy to run, assign. You can run your SOM directly from your PCA. So I went from this thought flow result to running this one, and then boom, you're out the door ready to go. Let me show you just some faults. So I'm going to open up this one, and I'll go view in 3D Viewer. So these are some fault results I ran, and they're pretty decent, but let me show you the data that I used to train it. So you can see here I got some faults coming through pretty well. This is just a small little subcube. And it started with, it's really easy to add data. So we have this left side. I'm going to click on golden. That's the survey. I'm going to click on amplitudes. Now I can add a line. So let's go to line 40. I'm going to add a line. Turn off this volume. And that is my line, right? So you can see my faults that I ran. I can edit polygons. I'm gonna load a polygon set that I ran. Polygon set. Golden fault demo. You can also create polygons really easily. You go to edit polygons, it'll allow you to create a new set. So there you can see all the different fault polygons that I ran here, right? So you can see that I digitized my faults actually on this line. You can see my very, very poor manual interpretation that I've done, but I've just to show a demo of how quickly you can make faults. So I digitized some polygons there. Now you can go into our other thought flow. So machine learning is how we run all our thought flow. Let's reset. Deep learning fault detection, build a new engine, time, survey. I know I want to use golden, so we go here. Limiter. You can also, we work in something called workspaces, so it's our 3D constrained areas. So golden's here, you can go filter by the map. So that's my gold, actually that's Niobrara. Let's zoom into that, zoom this item. So here's golden, way down here in Mexico. So that's my golden data set. Click amplitudes, okay. Choose where you want to train your data delimiters. Choose between a different time interest or inline crossline, and then you select your training polygons. So here's my golden polygon set with all my polygons. Move this over, you can see which ones you want to train on. So I want to train on this inline, inline 80, inline 40, inline 120, inline 100, so you can see which inlines you have interpretation on when you go to train. Select training parameters, and then you click OK, and you launch. Right, so this is how you build your predictive model. After this runs, you come back here to two-step process. I'm then going to choose that predictive model. So like golden fault engine using default. Okay. I'm going to train on golden. So you can train on one survey and classify on another. That works too. Click OK. And then here's the advanced fault workflow. So what this does is you can run the advanced fault workflow, which is going to run 2 iterations of pre-processing, preconditioning already, and then 2 iterations of post-processing. So this is like, it's going to do a dip filter, a structural-oriented filter, some post-processing, a preconditioning cleanup, run your faults, and then some post-processing fault enhancements on the actual fault probability cubes to make more continuous faults and clean up the fault data. Click run, and then launch, right? And so what I'm showing you is the actual output of that. So from that training, you can see that it did a pretty good job of actual fault prediction. So we actually have another volume that in here called the merge, fault skeletonized merged right here. I'll add an inline of this. So this is actually a merged amplitude volume of your faults and your amplitude. So you can see this is where the fault prediction was. I'll make it a little less hot so that you can see those faults will pop out pretty good. All right, so those are my faults that this model predicted. And like I said, I only digitized 5 lines. It took me about 5 minutes or less. And it did a pretty good job, right? Based off, compared to manual interpretation, having to do all these yourself, right? Pretty good job of actually predicting faults. So I'm now going to show you all lithofacies prediction. And let me bring up the Niobrara formation. So I'm going to filter on workspace. Change the color now. Let me bring in the amplitude too, so you all have a reference. And I'll bring in some wells. So when you load your wells, there's sometimes a lot of wells in a project. right? So these are all the wells in my workspace that I'm using. And you can save subsets. So I'm just going to show 3 wells. So I've saved these as part of a well subset. So I know I only want to work with these 3 wells right now. So this is a self-organizing map of the Niobrara Formation, right? So let me see if I can zoom in. And the song is pretty cool. You can see, I'll go on cross line this way, you can see it's going to capture all this stratigraphy, all of these faults. So you can clearly tell there's some faults going through here, even though this doesn't use any of the CNN fault data. You see with the stratigraphic layers are kind of falling out of, you can see them falling into place across this whole stratigraphic unit, right? Now, I go down here and I see that I have my color selector. Now each of these neurons represents similar seismic attributes that I used in my SOM analysis, right? So these invert, so I isolated a few neurons. Right? So one of the bigger questions we've had over the years is, what do my neurons mean, right? Like how do I use this to assign lithofacies or try to assign an actual rock property to these neurons, right? So that's one of the big questions. Before lithophase prediction, you do all your interpretation using this volume. And the user had to come in and look at which neurons mean what, and they'd have to make a judgment call over which neurons are what lithologies. But now we've had this integrated lithophase prediction. So I'm going to go over here to wells, and I'm going to open a new well cross-section. I'm going to add some wells, so I'm going to add some wells. And I already told you we can save subsets, so let me add my subset of these 3 wells. Right, and now from here, there's a lot of things you can do. Let's add a track, so let's look for effective porosity. I can come in here, add my effective porosity curve, change the curve properties. Right, so I want to fill it to 0.06 visible to baseline. And all right, now I'm going to fill. That's my greater than 6% porosity just filled. So you can keep adding all these tracks, et cetera, and you can add all these curves, change it. Then you can save it as a well template. So if you save it as a well template, you can then apply this template and then make your wells all look good. So I'm going to go here, open a template I've already saved, apply it to all my wells, and it's going to automatically set up my well cross section to be exactly what I want it to be. I'm going to flatten on a top, so let's flatten on this C bench. And you guys will recognize this from the demo that I showed, right? So I have my effective porosity curve, my volume of calcite, my shale, my dolomite curve, my lithofacies log, my SOM that I extracted at the wellbore. So if I go to my 3D viewer, what you're looking at is this self-organizing map extracted at these 3 well locations. And my seismic trace. So let me show you how easy it is to do lithofacies prediction. Right, so we have this new tool called Well Analysis. I'm launching it directly from the well cross-section. And I want you guys to take a minute. This is the first step, is just to confirm your data. So you see I had 2 different classification logs. I have my 4 facies cut off with the dolostone and my self-organizing map. And if I go here, you can see these are my class logs, my facies and my self-organizing map. And then I have all of my continuous logs, my effective porosity, my volume of calcite, my shale volume fraction, and my volume of dolostone. Then you finally have at the bottom all of your final well tables, your final QC. Sometimes you have additional logs that, like you might have multiple gamma ray copies or something like that, and you want to choose between them. Like you have a corrected, you can choose the corrected in here. But it's really easy. I can add a well log, so let's add a well log. I'll add gamma ray just because I'm talking about it. And then it automatically populates your well table, and you can choose, say I want to use the DF gamma ray, because that was processed by a company called Digital Formations, right? So they processed gamma ray for us, and I'm going to use Digital Formations gamma ray. But see, it's really easy for you to add logs and do this whole comprehensive analysis. All right, I'm going to go to Analysis Setup, And I'm going to do lithofaces prediction. Now, if you didn't have a lith log, if I didn't have a lithology log, this dolostone log, you can create it here. And there's a lot of ways to create it. You can also bring it in from Petrel. So you have a rock physicist who's actually looking at borehole, like drilling samples, like rock samples, and they define a class log, and you want to use it, you can use that too. You don't have to use our lithofaces log or our classification log. You can bring in any different classification log from Petrel or any other interpretation package, and you can use that to do lithophase prediction. You don't have to use our tools. It's just we give you the option to build lithology logs directly in the product if you want to use those. Yeah, a lot of different ways you can do it. So I can do lithofaces on the fly, right? So if I really want to do lithofaces on the fly, I can call this porous carbonate, right? A porous carbonate was an effective porosity greater than 6%, volume of calcite greater than 50%. I don't really care about the other ones, and I'll call this one green, right? I then can also go to make a copy, and I'll call this one tight carbonate, right? And I'm going to make tight carbonate is also high volume of calcite, but we'll make it less than 6%. Right? So you can do cutoffs too. You don't have to do a lith log. You can do essentially building a lithofaces log on the fly, so you can do parameter testing. And you can save these as a rule set, or you can load a rule set just showing you on the fly, boom, done, right? But I already built one, so I'm just going to use the lithofaces log that I already built. So I'm going to hit compute. So this is what you guys have seen before, right? This is the lithofaces prediction dashboard. There's a lot of information here, so let me go through it. These are the lithofaces fit statistics. So this shows you a little tooltip what each one means. We have intersection over union, IOU, which is a measure of how well it goes. Intersection over union is a machine learning measure of how well your predictive model fit your ground truth. And where intersection over union, it punishes both false positives and false negatives. Percentage fit is a measure of how many true positives there are divided by true positives plus false negatives. What that means is, say you're on your reservoir, and you have a high percent fit, it means that for wherever the reservoir occurred along your wellbore, it had a really, really high percentage fit to a neuron. Now, if you have your intersection over union low, while your percentage fit is high, it means that yes, it did a good job predicting, but you might have a lot of extra false positives. So that's how the balance of these two metrics kind of goes in sync. You want it to be a good predictor, but you don't want it over predicting, otherwise you can't trust the result. So you have all these fit statistics. And Kramer's V is really what we key off of. Kramer's V is a measure of statistical fit between two categorical variables. So if you have a high Kramer's V, you have a good chance you have a really good fit. And this is a 0.524. That's a really, really good Kramer's V value. Anything between 0.35 and 0.6 is a reasonable result. And if you're above a 0.6, it's a fantastic result, right? But we have a 0.524, which is a pretty darn good result for a Kramer's V. You have the lithofaces hit count. So we talked about 44, 78. It occurred 80 times. 78 of those 80 times were limestone. So if I go how many times limestone showed up, there's neuron 44 right there. So neuron 44, 78 times limestone and 2 times chalk. Now you can also do probability, right? So based off that, it's 78 divided by 80, so a 98% probability that neuron 44 is limestone. Now neurons 37 right here, 86% probability, so it's 42 hits of limestone, 4 hits of dolostone, 3 of unclassified. This is the probability, so this is based using my cutoffs on the fly. And this honeycomb is represented, it's called the Geophysical honeycomb, and it's an encoded probability. So I mentioned if it's a high dark color, that means it's a higher probability. So like neuron 44, this is a very dark color. It means it was a really, really good fit of limestone. 37, slightly lighter, it's a slightly lower probability limestone. Now if I go to other ones that are shaded lighter, it means that the probability was a lot lower, right? So if I go to, let's say, neuron here, neuron 12, all right? I'll go find neuron 12 in my table. It was a 18% unclassified, 56% porous carbonate, or my chalk, 21% limestone, 2% shale, and 3% dolostone. So I did a few samples, a little mix of everything here. See one shale sample. Now, it's going to be, the winner was porous carbonate with 56%, but because it was, I'm going to give it 12, only 50%, 56%, it's going to be shaded a lot lighter white, or lighter green, right? So it's a way for you to see which are high probability neurons. You also have all of these per lithofacies volumes. So I have, here's my heat map for porous carbonate, so hit count and probability. Limestone hit count and probability. Shale hit count and shale probability. And actually can generate 3D volumes right here. So I can load all of my different probability cubes and actually generate 3D volumes directly from this. What I'm going to show you right now is I'm going to save this as a color map, 8x8 demo. So this is one of my demo that I'm doing. And hit save. And I go here, and now I can apply that color map directly here. So mi demo. Let me make this full. Actually, here I'll go result set. I'll load an inline so it's easier to see. What's going on with you? Link cut, there it is. Off the volume. And now you can see, I'm going to zoom in, and you can see that expected section. So now I've turned my self-organizing map into an actual facies classification. Right, and I can go here, let me turn this back on. I can go to my color selector. And yeah, I can isolate the neurons. I've already done this clearly, you can see that make up a particular section. So I can turn the volume off, and you'll see these same neurons highlighted along my section. So I identified my A bench and B bench chalk, and you see which neurons represent that, right? This is the 2D color map where you can highlight individual neurons on the section, or in 3D. So I can show color selector. I've identified my chalk neurons. I can go generate geobodies now directly from the 3D viewer. And now, okay, geobody parameters. I can choose which neurons I want. Click OK, and now I get actual 3D geobodies of these particular neurons of interest, right? So you could do this for any of them, paste hand, net reservoir, etc., etc. So that's how you generate your actual geobodies. I told you we have this well analysis tool which allows you to do a comprehensive well analysis. So how did I even come up with these cutoffs, for example, to define my lithofacies? So within this, you have this now analytical dashboard. So let's go to new analysis. All right, so I want to look at the distributions of well logs within particular zones of interest. So let's look at the A bench. So I want to go A bench top, or we'll do B bench. B bench is the main reservoir. So we'll do B bench top to B bench base. You'll notice here that everything's auto-populated. If you want to manually change it, you can, but we're going to key off this formation top. It has the MD value there, so sometimes you have multiple picks of the same unit along a well, so you can make sure you get the right pick. And I'm going to do my analysis within this zone. So I'm going to continue to analysis setup. I want to look at the histogram. And let's look at effective porosity. 0 to 20%. So here's my effective porosity distribution for this zone of interest. So my B bench chalk, I want to look at the effective porosity of this. So I can right click and I can rename this to effective, I'll change this to B bench effective porosity. Save. Right, now let's do the exact same thing, but now let's look at make a copy. You gotta go to new analysis, but if you really want to make it easy, just make a copy. It'll make an exact copy of the last analysis. Let's do this exact same thing, but let's do it for the Fort Hayes limestone that we're talking about. So I'll go from the upper Fort Hayes to the top of the Codell formation. Let's see, Codell top combined. There we go. And I'll click update the analysis. I'll make this 0 to 20%. Now rename. All right, so now you can look at the porosity between these two zones. This helped me define my cutoff. So I'm sitting here, I'm like, wow, it's a pretty good break at about, I don't know, 6% porosity, right? So I'm going to use this information to define my lithofacies. My chalks and my B-bench have a 6% porosity, and my Fort Hayes has or greater than 6, my Fort Hayes has a lighter, or less than 6. So you can sit here and do a fully comprehensive analysis of your data. So let's look at the B-bench again. And I want to look at which neurons exist in that particular zone. So there's another way to find what are the key neurons that exist even within my formation tops. So I'm going to go here, Niobrara demo, and this is telling me right here that these particular neurons exist within this formation top. So I have neuron 34, 41, 49, and 50. Where are we at? Are we upper Fort Hayes or B-bench? We're B-bench. Okay. Update. Yeah, so these are the neurons that exist within the B-bench of the Niobrara. Alright, so now let's do a lithophase prediction only within the B-bench. I'm gonna narrow down my zone even more. Alright, so let's go. I don't want to do. Sorry, I'll do that. No, we can do that. That's fine. We'll go here, and I want to change the analysis, lithophase prediction. Discrete log. Let's go to 4 faces Dolostone. Ooh, not that one. Oh, the Dolostone doesn't exist in this layer, so that actually makes sense. And then this and compute. So now, this is interesting. So I had all of these neurons within this zone. So this is now only looking at between my B bench. And what this tells me is, yeah, neuron 26 showed up in my reservoir zone, but it wasn't a chalk. So when I go to make geobodies, I want to ignore neuron 26. All right, so I can go here. I can save this as a color map, and I'll call this 8x8 demo B bench. Save it, and now I can go here, load that 8x8 demo B bench, and boom, you can see those exact neurons kind of highlighted. So I was just able to isolate my B-bench chalk, which is the main producer of the field. Show my color selector. I'm going to click, 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 invert, generate geobodies. Generate geobodies. Was it the same ones? 47 to, no, one more time. So generate geobodies. I'd like to reset, yes. Okay. Generate geobodies. You can actually group them together. So I can treat this as a single lithofacies by going 34, 41, 49 to 50, and 57. Click OK. It's going to merge all those neurons together. And then I can run geobodies. Now I have a full geobody that is only representative of my B-bench chalk, which you can then run volumetrics on. So this is how you kind of integrate all of the different features together using lithophase prediction to make a model of your reservoir. Now, I don't have the West Desert example, but the one I showed, we have the nice paste in and a nice wet sand. You do that exact same thing here.